Good day, everyone. My name is David Williams, Executive Director of the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled The Thirst for Power, the Nexus on Climate Change, Water Scarcity, and Electricity Outage. We are grateful to Dr. Lin Zhang from the City University of Hong Kong for today's timely discussion. But first, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services that you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speaker. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for the panelists, please click the Q&A button at the bottom of your Zoom window and type your question. We've allocated sufficient time at the end of this webinar to address your questions. And now I'd like to introduce you to our presenter, Dr. Lin Zhang, Assistant Professor in the School of Energy and Environment at the City University of Hong Kong. Lin, over to you.
Thank you, David, for the very nice introduction. So let me share my screen first. Okay, can you see?
Yes.
Good. So as you can see from the title, today's presentation or seminar will be on a topic related to climate change, water scarcity, and electricity shortage. So this is a joint work with my previous PhD student, An Yang. If you are now in the hot zones or in the southern part of China, you will see this kind of warning signal saying that the temperature these days are extremely high, above 37 Celsius degree, then this will be a warning for the heat wave. So we now can feel this kind of climate change and global warming. Actually, a change in climate can be felt primarily through a change in water. Climate change actually is disrupting the weather patterns, leading to extreme weather events, unpredictable water availability, exacerbating water scarcity. So all of these impacts can drastically affect the water in terms of quality and quantity. If you look at China, although we have a large landscape, but there's a lot of resource problems also with limited water resources in China. If we see the water resources available per capita levels, you can see that China actually ranked 104 around 180 countries. So it's extremely low in terms of per capita level of water resources. The total amount of water resources in China is well below the world average. So water resource actually is not that ample in China, so there will be a problem. And what makes these things more severe is that in China, actually, if you look at the statistics about the surface water and total water resources in the last 10 years, or compared to the half century of the last century, you will see there's a significant decline of this water resources. And the water problem in China mainly due to two reasons. One reason is because the uneven distribution of the water resources in time and space, and the other is because of the inconsistent combination of water and land resources. Because the water used mostly is for a agricultural product, right? Irrigation. So the land resources will be highly correlated with the water uses, and also in recent years, because of the urbanization, the rapid increase of water demand also has brought very serious contradiction between the water supply and demand. And now we know that climate change has the potential to impose additional pressures. If you look at the left figure, this is a figure reported by a paper published in Nature, it shows the observed interannual variation of the water in two main rivers in China, the Yangtze River and Yellow River. The upper panel shows the water resources in the Yangtze River. Also, there's a currently slightly increased trend, but this trend is insignificant. But you look at the bottom panel, it shows a significant decline of the annual stream flow. It shows there's a decreased water in the Yellow Rivers. So they claim in that paper showing that the decline of these water resources in the Yellow River is mostly because of the climate change. And if you look at the right panel of the figure shown here, you will see that the map. This is the map of the major rivers and the watershed in China. So if you look at the colors, the increasing darkness in this map actually indicates the decreasing annual per capita water availability. You will see that's the northern part of China and also the coastal regions, they have a declining annual per capita water availability. But all these regions are with plenty of populations and a lot of industry and economic sectors. If we can classify the whole China by the basin, we can classify the whole China into 7 different regions based on the basins. And we look at some statistics. This statistic shows the water endowment and some climate conditions in these regions from 2002 to 2016. And it shows the distribution of the endowment across geographical locations in China. So we can observe significant regional heterogeneity, right? According, based on these natural resources and also based on the climate conditions. The major water resources in the northwest region concentration in Qinghai province and the precipitation levels. And we can see there's a quite similar trend between the precipitation, temperature, and growing conditions. And this temperature, the temperature and growing conditions actually follow the same trend as regional rainfalls. Growing degree days is the number of hours, the number of days that are suitable for farming or for agricultural planting. So these are the good days for agricultural sector. So the growing degree actually reflect the extent of suitability of a region to produce certain crops. However, these 4 figures actually indicate these regions are now experiencing scarcer water endowment and the weather is getting worse. And it's therefore particularly important to assess this uneven climate change in how this will influence the regional economy. And to know that, we know that the economy, most of our economy is powered by electricity, right? So we want to see how this water resources will affect electricity production and how this electricity production will affect the economy. And this is a recent paper we published in Applied Economics in showing we calculate the water use efficiencies across different regions in China. And we can see that surprisingly, the water use efficiency is extremely low for the regions with relatively high economic development, right? So for those regions, they use more waters, but the water efficiency is not that high. So that's also another problem. So the central government of China, they issued a water-related policy, so-called 3 red lines. The first red line is to control water resource, to control the overexploitation or utilization. And the second line is more to control the water efficiency. And the third line is to control the pollutant into the functional water areas. This is to control the quality of waters, right? Okay. So these are several projects we have conducted in our group to work on this water resources management. We can see the efficiency transition of the national situation of water uses, and also we can see the agricultural sector where the water rights trading is one of the major policies to tackle the issues, and also the industrial water mainly focus on the wastewater use and policy induced in structural change. And in today's seminar, I will mainly focus on the power sectors. We would like to see how the climate change induces water scarcity and how this water scarcity will affect the electricity supply, in particular on the different technologies used to generate electricity. If you look at this figure, the vertical axis is the Palmer Drought Severity Index, the PDSI. This is an index to show the severity of drought is ranged from -10 to +10. The negative value shows the drought, and the positive value shows the water abundance. Okay, so you will see that over the years, we can see most of the time the PDSI index is below zero. Below zero meaning there's a problem with water shortage in China. Right? Above zero means the water is reasonably okay, water resources. And we can further do some very simple analysis to show how this linked with the electricity generation. The horizontal axis again is the PDSI, the indicator for water shortage. And the vertical axis is the total electricity generation in China. We can see there's a kind of positive relationship between PDSI and electricity generation, right? Remember, the higher PDSI means the water abundance, the lower PDSI means the water shortage, right? Okay, so this relationship simply saying there's a kind of a correlation when the there's a water shortage, electricity generation will decline. Right? So we would like to know why. But before we go to more rigorous analysis, I would like to provide some media news from both China and US. So sorry for those who cannot read Chinese. So for this news is showing that there will be a drought that induces electricity supply shortage in Hainan, a province in China. And this is another news showing that drought induces electricity severe shortage in 5 provinces in South China. And again, we see a lot because of heat waves. This induces high electricity demand, and this high electricity demand will result in limited, restricted electricity supply in certain regions in China. And this, again, this is in 2019, which is about two years ago. And here, because of the drought, is induced the limited electricity supply will significantly affect manufacturing. So these are the news from China. And in the US, we also see there's a lot of regions with electricity outage, right? For example, the Michigan, the New York regions. And we also see some articles or news to talk about the California rolling blackout. And some of articles saying this rolling blackout is mainly because of climate change, one of the major issues. And another issue is because of the poor planning. And also climate change and really old grid because of the poor infrastructure in the States. This could be one of the reasons for the power outage. And also because the heat waves, people probably require more electricity, but with less supply. And this kind of a mismatch leads to the electricity outage. If you back to the story of China, if you look at this figure, this column shows the electricity generation over time. So we can see a clear trend that electricity generation, total electricity generation increases over time in China. And also these two dotted lines shows the growth of electricity generation by different sources, right? Okay, if you, for example, if you look at 2012, right, you can see there's a significant difference between the growth of electricity generation by using coal or hydro, right? But in the next year, 2013, you will see the significant decline of the growth of hydro, but a significant increase in the coal. So from this figure, you can simply have a feeling that there's a kind of a substitution between the investment in electricity for coal or investment in hydroelectricity generation. So that's kind of a substitution between these two technologies. So in this paper, in this project, what we would like to explore is want to know to what extent water scarcity will affect electricity generation technology mix, and how this electricity generation mix will explain electricity shortage in China. Actually, there's a lot of literature talking about this, and maybe they using, for example, some non-econometric approach, including life cycle assessment or engineering models or integrated assessment. So different from those papers in the literature, what we're doing is using an econometric model to identify the causal impact of the climate change induced water scarcity on electricity shortage. So in this case, this paper or this project will contribute to the understanding of the technology selection with restricted resource use input in the process of transition towards greener economy, right? Because in China now, the plan of the central government of China is to moving the economy towards greener and to lower the use of fossil fuels, and increasing the use of renewable energies. And secondly, this paper will contribute to the understanding how the government responds to climate change or to the climate shock. Because the power system, the power generation system is mainly controlled or managed by the central government and the regional government. It's a more state-owned system. So then how this technology use response to climate change reflect the government policy, government attitude on this. And third, this paper will identify the underlying mechanisms for this electricity shortage in China in the early 20s, and by linking water scarcity with electricity generation technology. So this will explain why this happens frequently in the early 20th centuries. And this will help us to preventing the happening of this electricity shortage in the later period. And if you look at this figure, the vertical axis shows the CO2 emissions and the CO2 emissions from electricity generation. So in general, we can see an increasing trend of CO2 emissions in China. So then, if the water scarcity will affect the technology used for electricity generation, then definitely will affect the CO2 emissions, right? So the second research question we would like to explore is what is the related environmental impacts? So these are the two research questions we discussed. So here is the spatial distribution of power plant we used in this analysis. It's about around 200 power plants across different regions in China. And this 200 power plant belongs to 7 power grid distribution network. Okay, they belong to 7 distribution network. So then later we will discuss how this network will be linked each other. Are they going to have a good help in order to relieve this electricity shortage, or there's some barriers between? Okay, the empirical strategy is quite simple. So left-hand side of the equation is the electricity generation per power plant. And in the right-hand side, we first have this water scarcity indicator. So and also times the fuel meaning the technology. So what kind of technology you use? You're using coal power plant generation, you're using hydro, you're using and nuclear. So these are the three major fuels used in China for electricity generation. So if we have these interaction terms, then we also control a set of control variables. This X control includes non-linear climate variables for example, green degree days, and also characteristics of power plants captured by, for example, installed capacity, indicators for electricity demand, and policies, fixed asset investment, and we also control a set of fixed effects, including the power plant fixed effect, power grid fixed effect, fuel type fixed effects, and time fixed effects. Okay, so how we can guess the indicator for water scarcity? So we obtained this monthly climate data from the National Center for Atmospheric Research, the Climate Data Guide, and National Oceanic Atmospheric Administrations. And they provide a global level PDSI. This is an indicator for drought, for water shortage. It's, again, as I mentioned, it's ranged from -10 to +10. The negative values demonstrate water scarcity, and we normalize this to based on this strategy. Alternatively, we can also using SPI. SPI is also account for the effect of precipitation reference evaporation. So both PDSI and SPI, they actually capture more long-term water shortage, while their precipitation capture the short-term water shortage is reflect the instantaneous water availability of plant surroundings. Why we choose PDSI and using this SPI and precipitation as alternative indicator is because a conditional on this seasonal trend, temperature, and other demand shock, the change in water scarcity by using PDSI can be considered as a possible exogenous shock to electricity generation. So, because its effects on electricity generation will be differentiated from the instantaneous weather patterns and the seasonal demand shocks. So in our identification strategy, we are free from these endogeneity issues. And to reflect the climate change, we introducing the cooling degree days, which is to capture the growing warming trend. And this cooling degree days, CDD, represents nonlinear measures of how surface air temperatures deviates from ambient indoor reference one. We use the reference temperature of 26 Celsius degree, as in other papers. Because we also want to see the environmental impact, we mainly focus on CO2 emissions, right? Because electricity generation is mostly to produce the CO2 emissions, carbon emissions. So we obtain these emissions from China emission account and data sets. And this consists of 47 production sectors and for different provinces and cities. Then we can allocate this to different locations. And we also control a lot of non-climate control variables, for example, the installed capacity, electricity price, investment. So that's the basic setting. Now, let's look at the baseline result. If you look at the first column, it shows the first column, the first row, it shows a negative but statistically significant impact, right? So remember that for PDSI, the lower values shows the water scarcity. The higher values shows the water abundance, right? So this means if there's a water shortage, PDSI declines, then the coal generation will increase because this is negative, right? It's negative. So water shortage will induce coal generation increase, but for the second row, it shows the positive and statistically significant coefficient for hydro, for the interaction term between PDSI and hydro, right? So this is correct. Because of the water shortage, then the hydroelectricity generation will decline. If there's more water, the hydroelectricity generation will increase, right? And we also find there is a negative correlation between nuclear and PDSI. So if there's a water shortage, then the power plant prefer to use more nuclear for electricity generation, right? So the first column controls for the plant fixed fact and year fixed fact. And in column 2 to column 4, we control different set of fixed facts. And we find most of the time the results remains. So the general findings from this baseline result shows that if there's a water shortage, the hydroelectricity generation technology will be reduced for electricity generation. But technology, the coal and the nuclear technology will be used more for electricity generation. How to interpret this? So if we look at the one standard deviation reduction in PDSI, this will result in about this 2 times 10 to the power 8 kilowatt-hour decline in hydro. But in the same time, we will see an increase in about 1.4 times 10 to the power 8 kilowatt-hours increase in nuclear and 0.28 times 10 to the power 8 kilowatt-hours increase in coal. So if we add up the nuclear increase and coal increase together, these will remain still lower than the decline in hydroelectric generation. So because of this water shortage, the reduced electricity generation from hydro cannot be fully compensated by the increased generation from coal and nuclear. So then this will lead to electricity shortage, supply shortage. Of course, we can use an alternative indicators, for example, using an SPI. As I mentioned, SPI is more similar to PDSI on the long-term drought or long-term water scarcity. So the results remain so saying that if there's a water shortage, the coal generation will increase negative again, right? But here we didn't see a significant impact of the precipitation because precipitation is mainly on a short-term instantaneous of the water availability. So this is consistent with our expectations. So here, so far, what we do is still using annual data, But we know there's a seasonal variations in terms of water resources, right? So in certain periods of time, there's a lot of water available, but in certain periods of time in a year, there's a decline in terms of water endowment. Right? We can also see these monthly variations, the seasonal variations, right? The PDSI in terms of PDSI and in terms of SPI. And we can also see these seasonal variations of precipitations and temperatures again, right? During summer times, there's an increase of the temperature and also increase of the precipitation. And in the winter time, there's a decline of the temperature and also decline in terms of a precipitation. So then next, we want to introducing these seasonal variations into our model. How we do this? Again, the left-hand side of the equation is still the electricity generation by time and by power plant. And this time, the time t is still year, but we introducing again in the right-hand side of the equation, you introducing the quarter index to show, because now the water scarcity indicator is a quarter indicator for each of the year. So which means in each of the year, we have 4 indicators, right? And then we can sum up this together to get the annual variations, to get the annual situations. Okay, let's look at this result. For this result, we can see there's a significant change in Q2 and Q3. So in Q2 and Q3, we can see there's a significant, if there is a water shortage, the hydro will decline, right? Because this is positive. If there's a water shortage, then the electricity generation from hydro will decline, but the electricity generation from coal will increase. These hydropower plants can take food. So, but in the winter times, right? But in the winter time, in Q1 or Q4, there's almost have no impact. Why? Because in the winter time, the hydropower plants can take full advantage of the stored water in the dam. So if they have the stored water in the dam, they are able to deal with the drought in Q1 and Q4. But in Q2 and Q3, the dam usually drains away waters. So they are not able to using the stored water in the dam to deal with the water shortage. Okay, so far, what we talk about is still kind of a linear relationship, right? So in the right-hand side is the PDSI index. In the left-hand side is the electricity generation. It's kind of a linear relationship. Now we want to know a more non-linear relationship, or the frequency of the drought. How this degree of drought severity will trigger different response to power plants. So in this case, we're introducing a model with bin specifications. So the specification is similar as before. One different is here, we're using the bin. In the right-hand side of the equation, we're using the bin. Here. This bin knows the number of months in a year on which monthly PDSI falls into the base level of drought severity bins in the climatic grid where the power plants is located. So here I'm using this figure to simply illustrate how we do this. So for example, we have there's a PDSI indicators, right? We can allocate, so now because PDSI is negative 10 to 10, but we can also, if there's a different indicator, we can range from negative infinity to positive infinity. So we can divide the whole range into 6 bins, okay? In each of the bins, we have some values for this, for example, PDSI indicators, right? So we can calculate how many months in a year is fall into, for example, bin 3, which is between -2 and 0. How many months in this bins? How many months in this bins? Then we are able to know the frequency of drought in a certain level of severity of water shortage, right? Okay. So by doing this, we can do regressions, and now we show the result. So this result shows by taking into account the frequencies. So how to interpret this? This shows we take this bin, this 2 to 5, this bin as the reference. So all the others are relatively to this one. So relative to this one, we can see with the severe of the water scarcity to the left-hand side of this figure, right? Then the electricity generation using coal plants will increase significantly. And this increase is nonlinear, right? The more severe of the water shortage and the increasing use of coal for electricity generation. Right? So first is relatively flat, now it becomes much steeper. So this kind of increasing use of coal for electricity generation because of the water shortage. And one, you may argue that our results can be driven several reasons. For example, one reason is because of the power plants, they have new built generation capacities, right? If there's a new generators in a certain power plants, this may drive our result. Okay, so we consider this in the column 1 and column 2. Okay, in column 1 and column 2, we can take into account the new generators. After we consider the new generators, we will see our main result still remains, right? Again, the coal will increase. The use of coal will increase because of drought, and hydro will decrease. Nuclear will also decrease. So now, after consider this new generator, our results still survive. So we can rule out this probability. A second possible reason may affect our results is because for a certain period of time, right, some power plants will regularly to do maintenance. To do maintenance, they have to just to shut down certain generators, right? If they shut down generators, some certain generators and these generators are consistent with our findings, then this may pollute our analysis, right? So we also take into account this maintenance, okay? After taking into account this maintenance, we will still see our main results survive, right? Coal use increase, hydro decrease, nuclear increase. Okay, so now we are more safe to say the result is consistent and robust, right? Water shortage will lead to decline in using hydro for electricity generation, but increase the use of coal and the increase of nuclear for electricity generation. Okay, next what we need to consider is the cooling technology and the water resources. So we know for electricity generation, it will use cooling technology. No matter coal generation or hydro generation or nuclear power plants, or they will have to use cooling technology, using water for cooling, but they're using different cooling technology. For coal power plants, they mainly use these two. One through technology and recirculating technology. They account for about 60%. And the other account for another 30%. And none account for 11%, and the other account for 2%. So this is based on the cooling technology, that distribution of the use of different cooling technologies. And also, the right-hand side of the table shows the water resources. So what kind of water sources you use for cooling? Right? You're using surface water, or using groundwater, or using municipal wastewater, or seawater. Okay. So we now look into these two types of technologies, how the water scarcity will affect the use of these two types of technologies for electricity generation. First, how does water scarcity affect the choice of technology for cooling? Okay. Again, we first look at the column 1. It shows that if we use one through technology, recirculating technology, when there is a water scarcity, these two cooling technology will increase. Well, again, negative, statistically significant. And we also know these two technologies mainly for coal power plant use, right? So this is consistent. Again, this is consistent with our baseline result. Okay, for non-hydro, right, is positive, and for nuclear again is negative. So this result confirms our baseline results. That water scarcity will induce the more use of coal power plants, nuclear power plants, but reduce the use of hydro. And column 2 to column 4, we also again control for different set of fixed effects, and the results remains. Next, we would like to know how this water scarcity will affect technology by water sources. Okay, water sources. So then we intact PDSI with different water sources: surface water, groundwater, municipal wastewater, seawaters. And we see the surface water is negative and statistically significant. This shows that if there's a water shortage, surface water will be used more for cooling. The groundwater is insignificant because in China there's a policy saying you cannot use groundwater for electricity generation. So this is consistent. And we see municipal wastewater is also increased. This technology is also increased for cooling purpose. And we didn't see a significant increase of the seawater. Okay, so far we talked about different technology in terms of the fuel, in terms of the cooling technologies, in terms of the water sources, right? Now we would like to explore the spatial effect of the water scarcity. Is there the below effect? So we discussed whether there's a spatial effect across regions through the intergrid transmission, right? As I mentioned previously, there are 6 grid distribution transmission systems, right? So if the power plants grid are well connected and free to transmit without barriers, we would expect water scarcity in one grid region could induce technology substitution in other grid regions, right? So for example, in my region, if there's a water shortage, right? If I cannot use hydro, probably I can import electricity from other regions where the water is abundant. Right? So to investigate these cross-region variations, we construct water scarcity indices for the 6 power grid by calculating the average values of PDSI for each of these 6 grids, and to verify the existence of spatial effects. And then we're using the new indicators, the new indices, to interact with the technology availability in other regions, in other 5 regions. Okay. So, for example, we first test whether water scarcity in the region where the South Power Grid, the SPGC, is located affect the technology mix. So we first look at the first columns. So the first columns we interact is the PDSI in the southern region grid regions. If there's a water scarcity happened here, how this will affect the electricity generation technologies in the other 5 regions, right? So we will see all these interactions, these PDIs interacts with electricity generation in other regions, that's mostly insignificant. So this confirms there's no spillover effect. There's no spatial effect over water scarcity through the intergrid transmission. So this result implies the inefficiency of the dispatch and transmission system in China's power grid network, right? Because if the power network, grid network is good enough, water shortage, the electricity shortage in one region can be resolved by import electricity from other regions, right? So then this result shows the inefficiency of the grid, of the national grid, and the lack of national barrier-free intergrid generation dispatch system could intensify the negative impact of water stress-induced electricity shortage. Okay, finally, we would like to know, how does water scarcity affect the environment? We can see mostly, again, we will see a significant impact of the water scarcity because water scarcity will induce significant increase of the coal generation, and coal generation will lead to more CO2 emissions, lead to more CO2 emissions. And we can also see this environmental impact is also non-linear. We can also do the bin specification regression for the CO2 emissions when we see that with the severe water scarcity and the CO2 emissions also increasingly pumped up, right? So there's a push up of the CO2 emissions with the most severe water scarcity. Okay. To conclude, so in this project, we analyzed the water scarcity, how the climate change induced water scarcity have impact on the electricity generations, in particular on the technology used for electricity generations. In terms of fuel technology, hydro will reduce, coal and nuclear will increase as a substitute. But this substitution cannot fully compensate the decline in hydro. So this leads to the electricity shortage. And in terms of cooling, once-through and recirculation, these two cooling technologies mostly used because these two technologies used for a coal power plant. And we also see the surface water and wastewater is used for cooling purpose. And at seasonal levels, we see a significant effect in Q2 and Q3, mostly in the summer seasons, right? That's why we frequently see this electricity shortage during the summer terms. And we also see this water scarcity will induce additional CO2 emissions as an increasing rate, right? So this is something we have to pay more attention to, right? Because now China is planning to moving towards more renewables, but because of the climate change, actually, climate change induced water scarcity will lead to the use of coal instead of hydro, instead of renewable energies. If this is something that needs to be taken into account when policymakers to plan to implement policy in the power sector. Okay, I think that's all I can share for today's seminar. Thank you. Now I would like to take the questions. Okay, I got two questions from the Q&A box. The first question, explain why you don't include May effects in your regression. May effect, what do you mean the May effect? So in my May regression, the left-hand side electricity generation, the right-hand side is the water scarcity indicators, right? So the May effect is how this water scarcity affects the electricity generation. So second, why groundwater cannot be used for electricity generation? I think that because the government issued a policy saying that the groundwater is not allowed for the use of electricity generation. Probably the reason is because the groundwater is to secure the regional water demand in other sectors as well, And also, if you're using more groundwater, then this will also probably affect the landscape, I don't know, and also probably affect the some physical reasons. Most of the data are publicly available. For the climate data PDSI, you are available. I think I already mentioned in my slides. Okay. So, so here for water scarcity indicators, you can obtain from these sources. And for example, these green degree days you can obtain from China's national data. And for CO2 emissions, you can receive from these sources. Yeah, for plant level data, yes, you can also obtain from the statistics, from some statistics. Yes. I think the national power sector, they issue this statistic every year with a published book. Did you test the possibility that drought may affect several regions, which may be a reason that's inefficiency on intergrids? You mean the drought simultaneously affects several regions? No, we didn't test this. What we do is to test for each of these 6 regions in return, and to see how the drought in one region, whether it will affect in other 5 regions or not. But we didn't test the simultaneous drought in several regions. Any other questions? If no more questions, then I would like to stop here. And thank you again for your listening. I'd like to hand over to Rebecca.
IAEE wishes to thank Dr. Lin Zhang for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not already a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.